Welcome back to our study of relativity, special relativity in particular, following the Queensland syllabus, and in particular the textbook written by Walding. So chapter 10, we're going to look at special relativity in terms of length, momentum, and energy, and we'll also have a look at some paradoxes and so on. And our images in this slide are from one of the coolest 80s movies ever, Back to the Future. So what are we looking at in this particular chapter? We're going to look at length contraction. We're going to compare mass and how mass changes as you move. We're going to look at some paradoxes around relativity and how where you're moving in one frame, another frame appears to be moving with respect to you. Look at some examples of this, of how this actually works in the real world, and have a look at what we can think about for our research investigation. We've got a number of formulae there. There's the length contraction one. All right, a little bit of velocity one, bit of a relativistic momentum. This one we've seen before anyway, so that's not too much of a big one. When you're revising, this is the Walding textbook. Have a look at chapter 9 and 10. There's some examples there on the screen there of some stuff to help you for your external exam. Particularly think about the 3-star questions. Think about your research investigation that's coming up. There's some little examples there of some sort of ideas that you might have to sort of shape your thinking a bit in order to do that task. Now, there is a game online called A Slower Speed of Light. There's some images there. This one here is what it actually looks like. It's actually a game. That's sort of the cover image for it. You can Google it online, find an example of it. Otherwise, it's in the OneDrive if you happen to be fortunate enough to be in my class. How lucky are you? Basically, it's a game where we sort of manipulate the speed of light, and it starts to change the environment around you. You've got to go around collecting these little orbs and so on in the game, and as you collect them, it starts to modify the speed of light. You have 100 of these orbs to collect, and the more you get, the more it starts to manipulate the environment around you, and you start to see the time dilation, the length contraction, and so on as you move around that particular area. I do really highly encourage you to go and check that one out. It is available anywhere online, just Google it. It's an interesting way to think about relativity. Here's a little thing to think about. In relativity, we replace something is with is measured to be. As we spoke about in the last chapter, time dilation is a real thing. The time that you experience if you're in motion or stationary is different. So it's not that we measure the time is this. The time is measured to be something depending on what your frame of reference is. So, chapter 10.1, length contraction. And this is all pictures from Back to the Future. That's part 2. The expectation versus reality thing there is really quite true. Back in the 80s, Michael J. Fox as Marty McFly was one of the coolest ones around. The kind of guy that, you know, every girl wants to be with and every guy wants to be. Whereas, unfortunately, this is what we ended up with in 2015. Hoverboards, I mean, I don't know. That's not a hoverboard. That's ridiculous. Anyway, let's go on. That's embarrassing. All right, let's frame our thinking here. Can we travel into the past or the future? And I did sort of mention this in the past, in a previous video. And the idea of the grandfather paradox. A person travels into the past, kills their own grandfather, which is before their father was conceived and born, or their mother was conceived and born, which means if your mother or father didn't exist, then you couldn't exist, hence couldn't go into the past to kill your own grandfather. And that's sort of an idea to sort of think, hang on, there's a lot of weird stuff going on here. There's an old book here, The Third Policeman, and in it there's this character, De Selby, who used mirrors to reflect his image backwards and forwards multiple times. Kind of like when you're in a bathroom or a room that's got mirrors on either wall, opposite walls. You can kind of almost feel like you're looking off into infinity. But with each reflection, it's an older and older image of you, hence it's a younger image of you. So what he said in the book was he needed a telescope to see the furthest or oldest images of himself. Hence, he could see his face as a young boy. Is this possible? Have a think. Is it possible? If you could look far enough into two mirrors opposite each other, could you see yourself as a young person? And the answer is obviously no, because the image only starts to form the moment you appear within those mirrors. So if you were born within those mirrors and you lived between those mirrors your whole life, then technically you could. However, the mirror is not 100% perfect and doesn't reflect 100% of the light, so there is some loss. But you can actually work out, based on the speed of light, if the mirrors, say, are a metre apart or 2 metres apart, you know the velocity is 3 by 10 to the 8th. You know the distance it's travelling. Hence, if a certain time passes, you can work out how many times the light will reflect off each mirror. It's a lot. Now, see, this is what I was talking about before. I mean, how cool is Marty McFly standing on top of a flying DeLorean time machine? I mean, I'm sure you're cool in your own world, but are you that cool? What are we doing today? We're going to look at space travel and, in particular, length contraction. And we're going to calculate proper length and relativistic length, just like we had before. Obviously, proper length, relativistic length, just like we had with time. That's meant to be a naught, by the way. So length contraction. The faster an object travels, the more its length contracts. It only works in the direction of travel. So if we look at our Starship Enterprise here, at rest, velocity 0, there's its proper length. But as it gets faster, so 0.2, for example, the speed of light, it's contracted a little bit. See how it's contracted a little bit from there? At 0.4, the speed of light, it's contracted even more. Almost 0.6, the speed of light, 0.8, 0.9, the speed of light. It would appear to be that thin. Notice in this direction, it hasn't contracted at all. It's only in the direction of motion, assuming it's traveling that way. If we look at another example of how this actually occurs, so here we've got the Stanford Linear Accelerator, Stanford in California in America. This is 3.2 kilometers long. You can look it up on Google Earth. You can see how it's a long path, that long straight path, 3.2 kilometers. But when the particles travel down that at that percentage the speed of light, this 3.2 kilometer track appears to be 1 meter long to those particles. That's what we're talking about with relativity. Everything's relative to your frame of motion. Here at rest sitting on Earth, you can look at that image there and see it's 3.2 k's long. But if you were traveling as a particle at 0.999999 the speed of light, that pathway appears to be 1 meter long to you. That's length contraction for you in the real world. Here's an example with some of these little interactives. Notice as they move the bar vertically and horizontally, it changes. Up here, you can see the bars are the same length, but when it goes vertical and horizontal, it contracts in the direction of motion. So we can see that those two spaceships in this example should be the same length, but because one's moving, it has contracted. Okay? Here's another example of length contraction. It's almost like that car appears shorter because it's traveling. The red and green line sort of show its motion in the direction of travel. So it appears to contract because it's traveling a very high percentage of the speed of light. There's another example there. At rest, that rocket is that length, and as it approaches the speed of light, it contracts. It only appears that way to us in our frame of reference. On the rocket, it wouldn't appear that way. It wouldn't appear to change because you are changing with the rocket. Here's another example. This wheel spinning around. Think of our circular motion. As it gets faster, at one point, those little yellow bars plus then will decrease in size to show that as they're traveling in the direction of motion, they're getting smaller and smaller. Like that. Let's look at another example. A trip to Rigel. Rigel's this character here is a star in Orion, Orion the Hunter. There's some images of it that we take of its region in space, and there's sort of a representation of what we think the star actually looks like if you could see it up close, like you could see our sun up close, for example. Now, if we travel to Rigel, it's 800 light years away. So if you travel at the speed of light to us here on Earth, that would take you 800 years to get there. So if you're leaving in 2020, when I'm filming this video, you won't get there until 2820 if you could leave now and travel at the speed of light the whole time. Here's a bit of bonus info about Rigel. Although he's 800 years from Earth, he's the brightest star in Orion, but it's actually 4 different stars together. All right, we're mainly seeing the supergiant Rigel. And there's a few distant dimmer stars with him. Much of its energy is emitted as UV light, but it's still 40,000 times brighter than our sun. So it's a very, very big, bright star. Now, because it's so big and bright, it's exhausting its fuel at a very, very quick rate. So these sorts of stars don't last more than a few million years. And hey, what's a few million years? Rigel's about 8 million years old, so we think that it's exhausted its supply of hydrogen and starting to get into fusing helium and heavier elements. Our sun's 4.5 billion years old and is going to continue for another 5 or 6 billion years fusing hydrogen. Rigel's only 8 million years old and has already used up its hydrogen. Over the next few million years, Rigel's going to expand and eventually it's going to become a red supergiant and explode into a supernova when it finally exhausts most of its fusion. When it does do that, it's going to be a very, very bright object in the sky if we're around to see it. After the moon, it would be the brightest object in the sky. Obviously, the sun is the brightest, the moon's the second brightest. It will be the next brightest. Now, let's have a think about going to Rigel. So, in the top one here, figure 2, as viewed from Earth, you can see that the rocket has that forward velocity. But if you are in figure 3 here and you are standing here on the rocket, it would appear that you're still. The Earth's moving away from you and Rigel is moving towards you. So it gives you an idea of what's actually going on here. It would appear that if you could measure the length, then on the rocket you are measuring relativistic length. On Earth, you are measuring the proper length between you and Rigel. And it's kind of in this context, last time I spoke about time and having 1 clock versus 2 clocks. This is almost like you are not undergoing any acceleration or any motion between you and Rigel. So hence, on Earth, that is the proper length between you and Rigel at rest. So let's look at our inertial reference frame between Earth and Rigel. Everybody agrees on the speed it's happening. There is a velocity here. The Earth-Rigel frame of reference is not in motion, so that's why they measure proper length. The Earth-Rigel system is measuring dilated time because it's almost like you need a clock here to measure the start and a clock here to measure when the actual rocket ends up there at Rigel. But if your inertial reference frame is the rocket, the velocity is the same, the speed hasn't changed, but the rocket is in motion, is accelerating away from Earth to reach that velocity. So we start to measure the relativistic length because you must accelerate up to that speed. You're measuring proper time because it's like you have 1 clock sitting here on the rocket and it's almost like Earth passes away from you and Rigel comes up to meet that clock, so hence you need 1 clock. That's why it's proper time. So let's have a think about how long it would actually take you. What would be the proper time? We've got our little table here with our numbers. So on Earth, you're measuring the relativistic time. On the spacecraft, you want to measure the proper time, and that's what we want to calculate. The distance is proper distance on Earth, relativistic length in the spacecraft. It will appear shorter length to you, which we'll come back to later, and the velocity is the same. So what do we know? We've got our formula for relativistic time from our last chapter. There's Marty McFly looking cool as in Back to the Future 3 in the Wild West. Being silly because he can't be told that he's chicken. You'll have to watch the movie. So if you can travel the 800 light years to Rigel at 0.999 the speed of light, how long would it appear to take you? What is the proper time? So the time here on Earth it would take you would be about 800 years. Your velocity is very fast, so we want to find this. Substitute those numbers in, pause the video and see if you can work out the answer. It'll take you about 35.8 years. That's time dilation. To you sitting on the rocket, travelling very close to the speed of light, 35.8 years would pass for you. But for everybody on Earth, 800 years would pass. You're travelling almost the speed of light. It's 800 light years away, so it'll take about 800 years for everybody on Earth. But to you, it's only 35.8 years. Now, let's see what we can work out of this. There's old Biff Tannen. Probably not the coolest character there, but anyway. That's Mad Dog Tannen, by the way, but he doesn't like being called that, so don't call him that. He'll get really upset with you like that and get a bit grumpy. Now, everybody's agreeing on the velocity. Earth Rigel system measures the proper length and the relativistic time. So, velocity is displacement over time. That's what that one's telling us. That's just velocity is displacement over time. It's just that the displacement is the proper length and the velocity we agree on is 0.999 speed of light. But on the rocket, we're going to use the same equation, but we've got different numbers. Velocity is relativistic length divided by proper time. If we rearrange that, we've got this here. What can we do with that equation? Where have we seen these terms before? We've seen that one before, and we have an equation for that one from our previous work. So you can substitute that in. Let's try it. So that's what we started with in the previous one. And we ended up at this point. So if we substitute in our formula for time dilation, we have that. Now let's see if we can start to rearrange this a little bit. We know that velocity times time, this bit here, relates to our previous equations on the previous slide, and that is the proper length. And what does it start to look like we have now? It looks like we have a similar formula to time dilation, but now we have one for length contraction. That's what we've ended up with. If that was a bit quick, go back and look at those numbers on the screen there, those formulas on the screen, and see if you can work it out again. Incidentally, with that one, think about how you can calculate the relativistic distance between Earth and Rigel travelling at 0.999 the speed of light. Go back and do that and see if you can work it out. Let's have a look at an example. Spaceship passes you at 0.8 speed of light. You measure its length to be 90 metres. Calculate the length it would be to observers on board the spaceship. So you're measuring it, it's passing you at 0.8 speed of light, and you measure its length to be 90 metres. So that would be contracted, so it must be longer in real life, like its actual proper length. So, because it's moving past you at 0.8 speed of light, you are measuring its relativistic length. You need to find its proper length. Here's our formula. We have our velocity, plug the numbers in. Its proper length is 150 metres. So if it was at rest next to you, it would be 150 metres long, but because it's travelling by you at 0.8 the speed of light, it only appears to be 90 metres long. That's length contraction in the direction of motion. There's a little extra bit for you to have a look at. Have a look at that, see if you can work out the answer. It's a bit of a challenge. I encourage you to do that to extend your knowledge. Now let's look at a different way to work out some of this stuff. Once again, Marty McFly in his time machine in the Wild West with Indians everywhere. Have you ever done that before? No. So when calculating travel time, time is the distance in light years divided by your speed. And that's just your velocity is distance over time equation rearranged. Your time will be in light years because we want everything in light years. Alright? If we're using speed and light years, the only time factor we have in there is years. So this will be in years. So, certain star is 36 light years away. Calculate how many years it would take a spacecraft travelling at 0.98 to reach that star from Earth as measured by an observer on Earth on the spacecraft. Calculate the distance travelled according to an observer on the space travel. So that's our relativistic length. And what will the people on the spacecraft calculate their speed to be? So let's have a look. So what do we know? The velocity is 0.98 the speed of light. The distance between Earth and the star is this proper length, 36 light years. So A, a little questions over the side here to remind yourself, how many years would it take the spacecraft on Earth? So an observer on Earth will measure the dilated time, like you need two clocks, one at the start and one at the end, so you measure the dilated time. And we've got a nice little formula that we use there. Velocity is the proper length divided by the time, which will be 36.73 light years. The traveller on the spacecraft will measure the proper time. We've got our formula for time dilation that we've used back in last chapter. Put in the numbers that you know. 36.73 years is how long the trip appears to take from Earth. Because you're travelling almost the speed of light and you're travelling for 36 years, because you're not quite travelling the speed of light, there's that extra 0.73 extra bit, so slightly over that. Plug those numbers in, it will take 7.3 years. So here on Earth, in our frame of reference, the trip's going to take 36 years, 36.73 years, but on the spaceship, because you've got time dilation and your time is contracted because you're travelling fast, the trip to you appears to take 7 years. That's what that calculation told us just there. In part B, calculate the distance travelled according to an observer. So here's our formula again. All right, now there's two different ways we're doing this. We've got our formula from that I used a couple of slides earlier, where you can use your length contraction formula. All right, we're working out how far it appears to travel. All right, the question says the distance travelled on the spacecraft. Because you're accelerating away from the Earth and getting towards this star 36 light years away, you're measuring relativistic length. Your length is going to contract, and that's what this formula will tell us. All right, and if you plug the numbers in, it comes out as 7.2 light years. So the funny thing about this is you're traveling 0.98 speed of light for 36 light years on Earth. On Earth, it'll take just over 36 light years. To you, it takes 7.3 years to do the trip. Sorry, on Earth it takes 36 years for you to do the trip. That was that one there. To you, it takes 7.3 years, and the distance you're travelling is 7.2 light years, is how far you appear to be travelling. And the last one, what do you calculate your speed to be as? Well, your speed should be the same because everybody agrees that the velocity of you with respect to the Earth star system is the same. So hence, here's a nice little formula to work that out for you. Length divided by dilated time, and give you 0.98, which will be the same. And it should be the same because everybody agrees the velocity is the same. All right, so let's just sum that up. On Earth, it appears that your trip takes 36.73 years because you're traveling 36 light years at almost the speed of light. But on a spaceship, what you need to do is use your time dilation formula and your length contraction formula, and it will appear that you're traveling 7.3 years and going about 7.2 light years. There's some further reading for you. I suggest you have a look at him. So let's have a review and check our understanding. When a car passes you on the road, is its length contracted? It is in motion with relative to you. Anything in motion will have length contraction in the direction of motion. So yes, instead of the car appearing like this, whoops, that's a really bad car, isn't it? It will appear contracted in the direction of motion, right? Physically shorter. Will you be able to see it? No, because its velocity is nowhere near the speed of light to detect these things. So, does it really contract or does it appear to contract? Yes, it will contract, but you won't notice it. Remember this example from last chapter about the muon experiment? The muons to us are traveling 1,910 meters in 23 microseconds, but because the length contracts to them, that's only 183 meters, and it appears to be 2.2 microseconds to them. So it will actually contract for the moving, for the objects in motion. So let's check our understanding here. A car travels past you at relativistic speed, which means really, really fast, approaching the speed of light. Not necessarily approaching the speed of light, it's moving past you at speed. What do you measure? What do you measure as far as the length and its symbol? Will you measure its rest length or its relativistic length? It's moving past you at speed. What you measure is number 3, the relativistic length. Because it's going past you, it will be relativistic length, and that is just L. It's not L naught because that's proper length. All right, you're not measuring it at rest. It's moving past you, so you will measure its relativistic length. All right, that's what we did today. We had a look at length contraction. We should be able to calculate the proper length and the relativistic length because we have our formulas now. Have a look at the check your learning questions. All right, we've done 2 of our equations there, the length contraction and the space travel relationships. Have a look at the next section before next time. Thanks for coming.